Hello everyone, I'm Adrija and welcome to the next video in this series. This one is on Euclidean algorithm. We'll be covering the following topics: the Euclidean algorithm, the extended Euclidean algorithm, the proof of these, and the time complexity and uses. So the aim is to be able to find the modular inverse, but we'll also go through linear Diophantine equations. And this is mainly a use of the extended Euclidean algorithm. The greatest common divisor, that's the main aim of this video. And given two numbers a and b, can you think of a good enough algorithm to find the GCD? So one very trivial and straightforward one would be to find the factors of each a and b individually and then compare them. But that's not very efficient. We want an efficient and a good algorithm, and for that we have the Euclidean algorithm. So the steps are that we initialize our first number a. So we have two numbers a and b. We want to find the greatest common divisor of both of these. We assign r0 to a and r1 to b and I to 1. And then we go through this division. So we divide the lower index 1 by the current index to get the quotient and the remainder, which is the next index. So r I minus 1, the previous index, will be the current index times the quotient. So we're dividing the previous index by the current index. We get this quotient and this remainder. So the conditions go like, if the remainder is 0, then GCD of A and B is this number, Ri, and the algorithm stops. If the remainder is not 0 and it's greater than 0 in that case, because the remainder has to be greater than equal to 0, so if it's not 0, it's greater than 0, then we increment I and we go back to step number 3. We go back to this step and we follow through. So this is what's actually happening in the algorithm. You have your previous index term, you're dividing that by the current index term, you're getting the quotient, and the next index term, which is the remainder. And then your I gets updated, then you're again dividing the previous index term by the current index term to get the next index term and the quotient. Again, I gets updated and it keeps going. Then we move on to the algorithm of the extended Euclidean algorithm. Okay, it's in short written as XGCD. And the extra thing that we're finding in that is that we're trying to write the GCD in this form, 8s plus bt, where a and b are the two numbers whose GCD we aim to find, and s and t are given that they're integers. Okay, so this is very useful. I've copied down the algorithm that was there on Wikipedia, like just a screen snap of that, of both the Euclidean algorithm and the extended Euclidean algorithm, just so that we can get a comparison. So in that, we just deal with r's. We set r0 to a, r1 to b, and this is the same thing that I had written there. In that case, ri minus 1 was ri plus 1 plus riqi. This term was on that side. And this inequality here says that the remainder, Ri plus 1, is smaller than the divisor. Yes. The difference between these two algorithms is that in the extended Euclidean algorithm, just like instead of just stating R not equal to A and R1 equal to B, we also initialize S0 and T0 and S1 and T1 values. And just as we have a recursion for R like this, where it involves dividing, we have a similar recursion for S using the same QI that we generated here. So in the extended Euclidean algorithm, we use the QIs in each step. Unlike in the normal Euclidean algorithm, we had no use of the quotients. We didn't have to actually divide it. All we needed to do was find the remainder. But here we need to properly divide it, get the quotient, and use that in finding the next terms in the S and the T series. This, just like the Euclidean algorithm, stops when rk plus 1 becomes 0, and rk then becomes the greatest common divisor, and these are known as Bezout coefficients, sk and tk. Rk, that is the GCD, can be written as a times sk plus b times tk. So that's where it stops. And just think about it yourself, how exactly this S and T recursion relations work. Now we move on to the time complexity, and we're trying to estimate the time complexity based on the number of steps. Yeah, so if we can figure out how many, get an approximation, pretty good approximation of the number of steps that will be required in finding the GCD, then we can have some idea about how complex the calculations are, all of that. So we proceed by this with this claim, and which we will prove in the future. So the claim is I plus 1 is less than Ri minus 1 by 2. If this is true, then we can write this inequality. That is R2k plus 1. I've just replaced I by 2k. So R2k plus 1 is less than 1 by 2 times R2k minus 1. And you keep going 1 by 2 square R2k minus 3. And so on, you keep going. If you raise this to the power of n, that is, you do the same thing n times, 1 by 2 to the power of n, what will come here? Pause the video and think about that. Okay. We get R2k minus 2n minus 1. Now we say that let the number of steps in our Euclidean algorithm be 2k, which implies that R2k is the GCD and R2k plus 1 is equal to 0. Also over here, replace n by k. So we get R2k plus 1 is less than 1 by 2 to the power of k now. R2k minus 2k minus 2k minus 1. Oh wait, minus should have been outside, my bad. So if we subtract this, you get 1 by 2 to the power of k r1, which is b by 2k. So r2k plus 1 is smaller than b by 2k. And note that r2k plus 1 is an integer. So for to ensure that r2k plus 1 is 0, we can say this is less than 1. And using that, we can get an approximation of this. So we can say b by 2 to the power of k is less than 1. Considering with this inequality, b is less than 2 to the power of k, and log b to the base 2 is less than k. So if we say k is log b to the base 2 plus 1, we get a pretty nice approximation. And log b to the base 2 is a number. We already know b, so it's easy to find that. And so the number of steps would be twice of this, but that's a pretty good approximation, and it's actually a very good time complexity. We will have another video on time complexity where we will see what is a good efficient algorithm, what is not. We'll compare those. Yes, next we move on to the claim Ri plus 1 is less than Ri minus 1 by 2. So Ri minus 1 is equal to Ri Qi plus Ri plus 1. You've seen this before. What we do now is we set Qi as 1. Note that Qi is the quotient, and when you're dividing two numbers, quotient can, when you're dividing a bigger number by a smaller number, quotient can only be greater than equal to 1. So when we set the quotient to be 1, we say that this expression is larger than this. Agreed? And we also know that the remainder is smaller than the divisor. So using these two, we again say that this expression Ri plus 1 is larger than 2 times Ri plus 1. And that's what we had to prove. Now we move on to the applications. Our aim is to find the modular inverse. We use the concept of linear Diophantine equations, which is finding solutions x and y of this kind of an equation. Ax plus by equal to c. Using the XGCD algorithm, we already had that AS plus BT is equal to GCD of A and B. So in this, if we just divide this expression by GCD of A and B and multiply into C, we get exactly that. So we already have solutions for X and Y. That's S times C divided by GCD and Y times C divided by GCD. These numbers satisfy. So we are finding solutions for this already. We use this in the concept of modular inverse. A inverse times A is congruent to 1 mod M. This inverse can be found by solving the congruence equation Ax congruent to 1 mod M. So right now we're saying A inverse as X. So this is the same congruency, just that A inverse is replaced by X. We want to find X. And the equivalent Diophantine equation for this is Ax plus My equal to 1. Why is that? Because if you just consider this expression, you're saying that one number ax, when divided by m, gives a remainder of 1. So ax can be written as m times q, some quotient, plus 1. So now we're just taking minus q and bringing it on this side, y as minus q, and we're writing ax plus my equal to 1, which is this. And that's it for this video. Thank you. Bye.